Today, many universities offer students the opportunity to take classes without physically attending the classroom or campus. This form of education, known as distance learning, is offered at many universities, including MIT, Berkeley, and Stanford. Oftentimes, distance learning is accomplished by making the materials available online. This includes notes, homeworks, and even lecture videos. At the same time, mobile devices are becoming more powerful and ubiquitous. For example, most modern cell phones are not only able to browse the web, but are also able to play videos. However, the screen size and resolution of a mobile device is not suitable for watching a lecture video. For example, the popular Apple iPhone can display a maximum resolution of 320 by 480. Furthermore, it has a screen size of 3.5 inches when measured diagonally. This can prove to be problematic when trying to read the small words on a lecture slide. For this reason, we propose the following solution. Magnify the significant portions of a slide when they are identified. The following video will illustrate this idea. In this video, a lecturer uses a green laser pointer to direct the viewer's attention to a particular portion of the slide in the video. The slide consists of a list of items, so when the laser identifies an item in the list, it would be optimal to magnify that item at that point in time. Our system modifies the original video so that an item in the slide is magnified when identified. Note that the magnified item is not a magnification of the video, but rather an enlarged version of the original slide image. This is a better solution than a simple magnification, as the item is free from discoloration or noise, as it is in the original video. Furthermore, as the laser point may be difficult to see in a small screen, we also redraw it as a red circle. In order to achieve this, we will need to answer the following questions. What is it we need to magnify, and when do we magnify it? In this case, we magnify bullet points, which we define to be an item on a list whose items start with a bullet symbol, number, or some other numbering scheme. We magnify a video when a laser is on a bullet point. To do this, we will need to know three things. 1. When and where a slide is shown in a video. That is, we need to find the homography for each video frame. 2. The coordinates of the laser points in the video. 3. The coordinates of the bullet points in a slide. So, what is a homography? A homography is a projective transformation. It describes how two images are related as seen by a pinhole camera. An example of a homographic transformation is shown below. The image on the left can be transformed to the image on the right. We use this transformation as it relates the slide in the video to the original slide image. To keep the video brief, we will omit the discussion on finding the homography and laser points. However, if you would like to learn more, the techniques are discussed in the listed papers. Now, we need to find the bounding boxes of each bullet in a slide. To do this, we will need to be able to read the PowerPoint file. However, our algorithm for finding bounding boxes only requires us to identify the bullet's text and color. In other words, if we know these two pieces of information, the algorithm can be applied to other presentations files as well. Our algorithm follows as such. We change the color of the bullet to a unique color. We do this twice and keep the two copies. Since the only difference between the two slides are the bullet's colors, then comparing the two will tell us the coordinates of the bounding boxes. Having found the bounding boxes, we need to know when to magnify the bullet. To do this, we observe the path of the laser points. The problem is that the laser coordinates were found with respect to the video frames, not the slides. To change them with respect to the slide's coordinate system, we simply apply the homography found earlier. A simple method of determining which bullet to magnify would be to simply count the box that contains the most laser points. However, as seen in this example, a circling gesture would be problematic as the laser points would be outside the box most of the time. We modify the naive algorithm by counting which box has the most laser segment intersections rather than laser points. This is done by creating a line segment between every two laser points in a small time interval. The line segments give us a sense of the path as well as the area of the laser points. For our experiments, they seem to be sufficient in determining which bullet needs to be magnified. Finally, we will modify the homography so that the bullet can be magnified to any video resolution. The initial homography transforms the slide from a 320 by 240 frame image to a 360 by 270 slide image. The small resolution is done so that the process of matching slides is fast. However, using a small slide image to magnify a bullet will cause it to be blurry. Changing the homography simply requires a change in scale and position so that the magnified bullet is centered around the original bullet's position. With this final computation, we are now able to magnify a bullet for any laser gestures found in the video.